The first approach for combinational synthesis we will discuss is the Karnaugh's method. The Karnaugh's method is an exact two-level combinational synthesis method. It is a graphical method based on the visual analysis of a table called Karnaugh map, making it easily usable by a human. Its application is simple for up to 4 variables, somewhat more laborious for 5 and 6 variables, and practically unfeasible for a larger number of variables, as it would require a multidimensional map. The method uses cardinality as the cost criterion. If the optimal solution is not unique, it utilizes the number of literals as a secondary selection criterion. The simplification strategy of the method consists of applying a specific reduction rule derived from the properties of algebra. Considering Z as any product term and A as a literal, the rule states that the expression in the form of a sum of products, A and Z, or not A and Z, can be transformed into Z and A or not A, which after simplifying the sum within the parentheses leads to a result equal to Z. To give an example, let's consider a function with 4 variables and an onset composed of 10 and 14. The first canonical form is thus A, B, C not D, or A not B, C not D. Between the two product terms, we can factor out A, C not D, which multiplies B or not B, which is equal to 1. Therefore, the final expression is A, C not D. The reduction rule shown here leads to a decrease in both the number of product terms and the number of literals. In the example, we went from 2 product terms to 1 and from 8 literals to 3. Moreover, the rule keeps the form of the expression unchanged. Expressions in the form of sums of products remain in that form. At most, the expression trivialized in a single product or a constant. The presented rule can be applied iteratively to more variables. In particular, the number of minterms involved is always a power of 2, such as 2, 4, 8, and so on, where the exponent of the power corresponds to the number of simplified variables. For example, let's consider the function with 4 variables having onsets, including 12, 13, 14, and 15. Starting from the first canonical form, we can apply the simplification rule to the first 2 terms and to the last 2. In each case, we factor out 2 product terms that multiply by not D or D, which can be simplified. Then, we can factor out AB from the remaining 2 product terms, which multiplies by not C or C, and this can also be simplified, resulting in AB. To summarize, we have simplified 2 variables, involving 4 minterms, that is 2 to the power of 2, and eventually obtaining only 1 product term. Note that we could have first factored out AB not D from the first and third minterms, and ABD from the second and fourth minterms. The result, again consisting of 2 product terms, can be reduced once more by simplifying not D or D, thus arriving at the same result AB. In conclusion, a different ordering of the variables during the iterative application of the reduction rule does not affect the final result, which is always the same. As we saw in the example, each application of the reduction rule results in a new product term with fewer literals, which generates the same ones of the function corresponding to the product terms we simplified. We assign the name implicant to this new product term. In general, the implicant is a product term in any expression in the form of a sum of products. It involves a subset of the variables of the function and corresponds to a subset of ones of the function. A minterm is therefore an implicant in which all the variables appear. Once an implicant can no longer be reduced, it is called a prime implicant. For example, let's consider the function analyzed in the previous slide. AB not C not D, AB not C, and ABD are 3 examples of implicants. AB not C not D is equal to 1 for minterm 12, AB not C is equal to 1 for minterms 12 and 13, while ABD is equal to 1 for minterms 14 and 15. AB is a prime implicant because there was no way to reduce it further. We can notice that it was the last implicant remaining in the expression. The goal of the Karnaugh method is to apply the simplification rule iteratively until only prime implicants are obtained. In the context of defining a synthesis method, the first problem encountered is finding a systematic approach to select pairs of implicants to be simplified. Two implicants form a reducible pair if they consist of the same variables and the Hamming distance between their respective binary configurations is equal to 1. The Hamming distance between two binary strings of equal length is the number of positions at which the corresponding symbols are different. For example, the Hamming distance between 0, 1, 0, 0, 1 and 1, 0, 1, 0, 1 is 3, as they differ in the first three positions from the left. Let's consider an example of calculating the Hamming distance between two implicants. Take the product terms ABC and AB0C. Their corresponding binary configurations are 1, 1, 1, since the first product consists of variables in their positive form, and 1, 0, 1, since in the second product, B appears in its negated form. The Hamming distance is 1, therefore the simplification rule can be applied. It may happen that the same implicant is involved in multiple pairing. Let us consider the following example, where we want to optimize the function with an onset including 1, 2, and 3. As you can see, AB can be simplified with not AB, generating B or A not B. Alternatively, AB can be simplified with A not B, leading to the result not A, B, or A. We have obtained two different results, neither of which is minimal and both of which can be further reduced. To overcome this issue, we can apply the idempotence property, that is A equal A or A, to replicate the implicant and use it in multiple simplifications. In this example, we can simplify in both ways shown above at the same time, thus obtaining the final form, B or A. Sometimes not all prime implicants generated during the application of the reduction rule are strictly necessary to build the final solution. Let's consider this example, where I quickly show how three prime implicants were generated using the method we have discussed so far. Not A not B covers minterms 0 and 1, not BC covers 1 and 5, and AC covers 5 and 7. We can see that selecting only not A not B and AC is sufficient to cover all the ones of the function, while not BC is redundant. Therefore, the optimal solution, considering cardinality, is not A, not B, or AC. In conclusion, in this module, we have identified a synthesis strategy to optimize an initial expression in its first canonical form. However, many questions remain open. In particular, how can we systematically select pairs of product terms and, more generally, sets of 2 to the power of n minterms to be reduced? Which minterms should be replicated using the idempotence property? How can we determine that further simplification is not possible and that we have obtained only prime implicants? Finally, how do we determine which prime implicants are necessary to construct the solution? And if multiple choices are possible, how do we select the best one? In the next modules, we will see how the Karnaugh's method systematically addresses all these questions.